Okay, so the inverse of a function, again, not unlike a composite function, it can be easily found, an actual rule. But does it exist? Well, there's some certain criteria have to be met. To find the actual inverse function, all we really do is interchange the x and the y values. Yeah? Interchange the x and the y and then solve it for y again. The notation we use, f inverse, f to the minus 1 of x. Okay, so f minus 1, it's not a power, okay? It's not to be confused with f of x to the power of minus 1, okay? It's f to the minus 1 of x. All right, so that's my inverse function, all right? So a couple of properties that we need to be aware of. Since our ordered pairs are interchanged and then we just solve it, obviously the domain of my inverse function, the set of x values, becomes now the set of y values and vice versa. So the domain of the inverse is the range of f. The range of the inverse is the domain of f. Okay, so the domain and the range swap. Graphically, my inverse function is a reflection about the line y equals x. So if I have a function here like this, my inverse function will be a reflection. All right, going the other way, always. Make y the subject. Here's the big kicker. Only one-to-one functions have an inverse. Okay, so if your function isn't one-to-one, the inverse, even though you can find a rule, doesn't exist. So more often than not, we have to restrict our function to make it one-to-one. All right. To find the point of intersection between f and f inverse, the point of intersection will always take place along the line y equals x. So again, let's come up with a different inverse function. So if I happen to have a function there like that, the inverse function might be like that. Okay, probably a bit squarer. So that point of intersection, you can either let f of x equal x, f inverse of x equal x, or f of x equal f inverse of x. So either of those three methods will find you the point of intersection. Invariably, it's easiest that way, okay, because the inverse function is often a little bit more complicated than just the function y equal to x, all right? The function f of f inverse of x, for much the same reason, is always equal to x. So if I substitute the inverse into the function, I get x as a value, all right? So there's some properties. There's some big key ones, why the inverse or how the inverse exists. So let's now try and find a few. So we can see here we've got the function 1 over x minus 2 plus 1, defined only between 2 and infinity. All right, so that would be the graph of that there. I've prepared this one earlier. So 1 shifts the graph up 1 unit, 2 shifts the graph to the right 2 units. On the axis, sketch the graph, label the asymptotes with their equation. X equals 2, y equals 1. There's the graph of the function. Now, normally, if we had sketched the whole graph, we would have something like, I don't know, something like that, yeah? Now, if I've got the whole graph there, that's not a one-to-one function, so the inverse wouldn't exist, which is why we've been asked to sketch the graph only on the right-hand side from 2 to infinity. So now my function is in fact one-to-one. So to find the rule and the domain of the inverse function h inverse, to find the rule, well, we know y equals, I might make it a bit bigger, y equals 1 over x minus 2 plus 1. Swap the x and the y values. And now rearrange. Get x minus 1 is equal to 1 over y minus 2. So we can, a couple of ways you can think about this. If I multiply the y minus 2 onto the other side, and then divide the 1 back. Which leaves me with y is equal to 1 over x minus 1 plus 2. That's why we must h inverse equals 1 over x minus 1 plus 2. Right, so there's my inverse function. Now if we have a look, the domain of this inverse function, we could have a look here. We could see you would expect it to be r except for 1, yeah? But if we have a look at the range of this graph, it's from 1 to infinity. I just realised I made an error before, didn't I? It would be from 1 to infinity. So the domain is not inclusive of 1 because we don't touch the axis. 1 to infinity. The range of f inverse, of h inverse, is equal to the domain of the original function, which is 2 to infinity. Okay, and if we have a look at the graph here, that sort of looks like that, doesn't it? Just, I'm sure you picked it up when I was talking about it. If I was to sketch the full graph, it wouldn't look, it was not a truncus at all, was it? So if I put x equal to 0, I get a half. So the full graph would actually look like that. Yeah. Which, as it turns out, is in fact a one-to-one function, so the inverse would still exist. Yeah, anyway, so a little error there on my behalf. So let's get rid of the rest of the original function. So what have we got? We had to find the rule. We've done that. We've stated the domain of the inverse function. Oh, we didn't have to get the range. All right. All right, let's move on. Find the inverse of the following functions and state the domain and range of the inverse. So as soon as you have to find a domain and range, I think it's often worthwhile to find them first. So for the domain of f, well, we need 2x plus 1 to be greater than or equal to 0. So x is going to be greater than or equal to negative a half. So there's the domain. And that's the square root function that hasn't been moved at all. So the range of f, including 0 to infinity. All right. So now let's find the inverse. So I swap the x and y. So I'm going to write x is equal to the square root of 2y plus 1, square both sides. X squared is equal to 2y plus 1. 2y is equal to x squared minus 1. So then y is equal to 1/2 of x squared minus 1. So given that, the domain of, I forgot my own cardinal sin, so it's an f, so f inverse is equal to 1/2 x squared minus 1. So the domain of f is equal to the range, which is 0 to infinity, f inverse I should say, and the range of f inverse is equal to the domain of f, which is from minus 1/2 to infinity. Okay, which kind of makes sense, isn't it? Because the graph of this is equal to 1/2 x squared minus a half. So it's a half x squared shifted a half unit down. So the range is going to be from negative half to infinity. All right. Similar process. We've just got where x is greater than or equal to 0. So if I sketch the graph, quick graph sketch, intercept there, intercept there. So it looks a little bit like that. Except we're only sketching it where x is greater than or equal to 0. So I'm only doing that section. All right. So the domain is clearly from 0 to infinity. And the range is going to be the same. So if I rearrange, I'm going to have x is equal to y squared plus 8y. So now I need to get y on its own, but we've got two representations of y there. So when we do that, I'm going to complete the square, halve it and square it, plus half 8 is 4, 16, minus 16. So now I can write this as x is equal to y plus 4 all squared minus 16. X plus 16 is equal to y plus 4 all squared. So y plus 4 is equal to plus or minus the square root of x plus 16. So y equals negative 4 plus or minus the square root of x plus 16. Bit tight for room. Let's make sure we put the inverse down. G inverse is equal to negative 4 plus or minus the square root of x plus 16. Now, there should be, and there will always be, enough information to let you know whether or not you're looking for negative 4 plus plus something or negative 4 minus something. Okay, so since the range of values is going to be from 0 to infinity, I don't want to subtract anything from negative 4. I want to add it. Yeah. So if I settle for G inverse equaling negative 4 plus the square root of x plus 16, the minimum, the domain is from 0 to infinity, because that's going to be the range of my, the range of G is the domain of G inverse. If I put x equal to 0 in, I get negative 4 plus the square root of 16, which is equal to 0, which will match off with my new range. So I've got the rule, the domain of the domain of G inverse is equal to the range, which is 0 to infinity, and the range of G inverse is equal to the domain of G, which is also 0 to infinity. So it's probably not the best example because the domain and the range happen to be the same values, but just make sure that that range there is going into that domain, and that domain there is going into that range. All right, one to go. A little bit of everything here. So we've got a couple of functions here. State whether or not the composite function exists. So step one, I hope you're saying to yourself, is let's draw a domain range table. So we've got domain range f, g. So we've got f, I've got the domain is from 0 to infinity. The domain of G is, I've done the order slightly different, haven't I? The domain of G is R plus. What about ranges? The range of f. So we've got x squared plus 2. So at x equal to 0, we've got y is equal to 2. And everything increases from there. And I've got e to the minus x. What does e to the minus x look like? It's that one, isn't it? Yeah, it's a reflection about that way. So r plus, that point there is from 1. So it's going to go from 0 to 1. Okay, does that seem about right? I think so. All right, whether or not g of f of x. So for g of f of x to exist, I need the range of f to be a subset of the domain of g. The range of f is from 2 to infinity, subset of the domain of g, which is r plus, which is true. So therefore exists. Does the inverse function exist for g? Well, I guess it does. Yes, but why? Since g is 1 to 1, find the rule in the domain of the inverse function of f. Okay, so we want f inverse, so we know that for f, y equals x squared plus 2, so x equals y squared plus 2, 2 y squared equals x minus 2, y equals plus or minus the square root of x minus 2. So we should be able to eliminate one of those plus or minuses. So the domain of f inverse is equal to the range of f, which we wrote down, and the range of f is from 2 to infinity, and the range of f inverse is equal to the domain of f, which is from 0 to infinity. So now we can finalise my function. Therefore, f inverse is equal to, now if I look at the range of f inverse, it's from 0 to infinity, so I want the positive values of x, square root of x minus 2. Okay. I hope that makes some sort of sense, so off you go. Big chapter exercise, so yeah, put plenty of time into it.